Welcome to our lecture on advanced machine learning in the Introduction to Machine Learning project. My name is Ben Bischel, and today we'll take a look at cost curves in our chapter here on imbalanced and cost-sensitive learning. So this will be a multi-part series. In this part here, we'll introduce cost curves as a tool to analyze the misclassification error in terms of varying prior probabilities for the positive class. We'll discuss the duality between points in ROC space. We'll figure out that for every point in ROC space with coordinates as false positive rate and true positive rate, there is an associated cost line in, I don't know, cost curve space, and vice versa. So we can transform these points to cost lines and back again. And we'll then also at the end figure out how from the multitude of different cost lines that are generated by us considering all of the hard label classifiers by varying the threshold of a probabilistic classifier, that this gives rise to a so-called lower envelope, and that will at the end give rise to the true cost curve. And in this part here we will only define this in terms of not really true costs and cost matrices, but just these misclassification errors, which will already be quite useful, and it's a first stepping stone to build the general thing, and then in the upcoming video we'll generalize this to true cost matrices. So let's start. So what's the idea behind cost curves? Well, kind of already foreshadowed this a bit. So we now want to directly plot the misclassification costs in terms of our prior probabilities. So we have some prior well, I guess now my pen tool is not working, so let me try to correct this. Does it work now? Well, it's now green. I guess, do I care about this? I guess I do. Let me change the color. Yeah, that works. Okay, so we have a prior probability pi plus. So this will just be the, I don't know, proportion of elements, kind of the size of our positive class. The larger this is, the more elements we have, or the more likely it is in our data generating process to sample an element from the positive class. And now what we want to do is we want to kind of directly plot the misclassification costs of a given classifier with respect to this setting of the prior probabilities. Of course, 1 minus pi plus is the counter probability is exactly the prior probability for the negative class. So as maybe I should have said that before, we'll analyze and introduce cost curves here in the scenario of imbalanced, cost-sensitive binary classification, but not for the multi-class case. And directly now plotting the misclassification costs in terms of this prior probability might be a little bit easier to interpret than ROC curves in terms of the costs or these priors. Here's kind of an example. So if we look at two different ROC curves for two different classifiers, we would have potentially F1 and F2 as two, I don't know, score-based or probabilistic classifiers. We calculate their respective ROC curves. We can see them here. So that's the curve for F1, that's the curve for F2. This guy here, this line is our kind of worst case scenario. So on this line we have all of the random classifiers which spit out labels with a certain random probability with any regard or reference to the features. So if we look at these curves, so I guess we can easily see that they cross. We know that the more they kind of lie towards this optimal point here in the upper left corner, the better they are. And for a certain region where the curve of F2, that would be this region here, is above the curve of F1, we know that in that region F2 dominates F1, and here kind of the situation flips, right? Unfortunately, we don't really see the thresholds. We could plot them into the thing. That wouldn't really be impossible. We can't really see how costs influence that. I guess that's a bit worse, or how class distributions influence that. I guess just like putting the threshold here at that point where that kind of flipping of the situation occurs wouldn't be impossible, or we could also plot the threshold at various points on both of these curves. That I guess we should do this in general, and many toolboxes allow this. But yeah, how varying costs and so on influence this dominating behavior is much less clear. Cost curves help here a bit. So how do we set them up? So first of all, I will not really discuss here cost curves based on true general cost matrices. We'll do that in the next part. Here we'll make one simplifying assumption, and that is, well, I guess the first one is not really truly a simplifying assumption, but I will assume that correct classifications, so if we produce a true positive or if we produce a true negative, carry zero costs. I guess that is a reasonable assumption. The next assumption, and that's much less realistic, but we just do this here for simplification purposes to get a nice easy starting point, is assuming that the costs of false negatives equal the costs of false positives. So obviously if these two numbers are equal, well, then we are basically back to just measuring misclassification costs up to a constant, and about this constant we usually don't care in optimization, or just like easily, I don't know, rescale it back to misclassification costs, right? So this is misclassification costs up to a constant. Pretty obvious. Now what we can now do is we can write down a nice simple formula for our performance measure misclassification error. So this is rho MCE. So rho was our usual symbol for a performance metric, and we write that down now as a function of the prior probability pi plus. So how can we compute this now? So how can we compute these misclassification errors? So I guess there's two cases to consider. So one case is we produce a positive example. So for that we have the probability pi plus in our data generating process, and now we multiply that with the conditional probability of assuming we have a positive class with a label of +1, but we produce a prediction of 0. And to that, obviously, we have to add the second case of sampling a negative example. So this would be pi minus, which is the same as 1 minus pi plus, times the conditional probability of we predict a +1, given that we are in the case of a negative example. Okay, so can we now simplify this formula? Answer is yes, we can. That's really easy. Let me remove maybe a couple of these scribblings here. So pretty obviously, this probability here, so probability of predicting a 1 under the assumption that the true class is a 0, or is negative, that's exactly our false positive rate, right? So we predict a positive element, but that was actually a mistake because the label is 0. And this guy here is obviously the false negative rate. And now we can rearrange terms a little bit, and what we end up with is a nice little formula for a straight line, where the slope of that straight line is given by the false negative rate minus the false positive rate, and the intercept is simply FPR. So what we now know is that we can write the cost line of a hard label classifier simply in terms of FNR and FPR. So if you give me access for a hard label classifier, if you just allow me to measure its FNR and its FPR, I can draw the line as a cost line by calculating the slope and by calculating the intercept, which is simply just FPR. Which means we can now really identify cost curves as point line duals of ROC curves. So I guess we haven't really talked about cost curves yet, but we can see the duality now between these cost lines and points in ROC space. So for example, we have a point like that here. So that is apparently a decision tree. We can measure its false positive rate and we can measure its true positive rate. So I guess, as these terms are always a little bit confusing, so I guess maybe let's write down our, oh no, I shouldn't do that. I should put the true classes into the columns. So we have something like this here, and we have predicted classes, which can also be a 0 and a 1. So actually maybe we did this. Well, let's fine. So here we have the true positives, here we have the false negatives, here we have the true negatives, and here I have the false positives. Yeah, it's predicted positive, but that's actually wrong. And now my head is in front of these of this little matrix, so I guess I have to move a little bit. So if we now look into this RC plot, what do we have here? So we have the true positive rate and we have the false positive rate. So false positive rate is this guy, and this is the rate here in this column, in this column. What we have also given is the true positive rate, but what we actually need is the false negative rate. But if we look into this column, so we can clearly see that F and R is simply 1 minus T. P, sorry, really bad at writing here on the iPad, is 1 minus TPR, right? It's just a counter probability in this column. So if we have a point here in our ROC space, we can directly convert this now into the cost line of our classifier, and obviously this also works vice versa, right? If you know the slope of such a guy, if you know the intercept of such a guy, you can easily go back, because the intercept is simply FPR, and then you identify the slope with FNR minus FPR, and you already know what FPR is, right? Because it's the intercept, so you do slope minus intercept, which gives you, I guess you do plus, right? Which gives you the false negative rate. And from the false negative rate, you can now compute the TPR. All of this is pretty trivial, so I guess I don't have to go through this a lot. So what we can now do is, for such hard-labeled classifiers, we can already plot their cost lines. And that might already be interesting to us, because we can now see how, if we change the prior probability for the positive class in our data generating process, we can see how misclassification costs change. That's already pretty nice. It's not, I don't know, rocket science, super complicated, but it's already pretty useful. A few more details on this. So here's again our equation for the cost line, simply copied over from the last slide. What we can now also do is we can kind of talk about a nice, simple visual construction of such a line, because what we know is, where does this line actually hit this axis here? So at the 0 point, so if pi plus is 0, this is simply FPR. So if you know the FPR of the classifier, you already know 1 point for your line. And I guess if we have already 2 points for our line, we can connect these 2 dots, and then the line is well defined. So I don't know, maybe we can take a look here at this blue guy. We know the FPR is 0.5, which means this is the first point on this line to visually construct it. Now, I guess I can also move again a little bit, and maybe should take good care not to again draw where my upper body here is located in the video. Now we just need a second point, and if you know, insert a 1 for this guy here, for pi plus, so we now want to kind of create a second point here for pi plus equals 1. So if pi plus is 1, so we have FPR minus FPR, so this cancels out. So we know that the second point here will simply be the false negative rate, which is 1 minus TPR. So if we are in the standard coordinates in rock space, we know that for the blue classifier number 2, the TPR is 0.7. We know that our second point is the FNR of 0.3. So we mark this here, we connect the 2 dots, and we are done. Okay. Also not super complicated. We can now also say that if one line is completely above the other, we can say that one of the classifiers, so in this instance here, the green guy completely dominates the other guy. And for the green and the blue guy, whose cost lines intersect, we kind of now know the operating range, or no, sorry, I shouldn't say operating range. We know the range of prior probabilities where classifier blue is better. Yeah? So this is left of, or where all of the prior probabilities are less than 0.4, and if they are larger than 0.4, then the green guy wins. Okay, good. So let's now, actually this looks a little bit like a typo here. Why does it say 0.7? I guess that really is a typo, and we should fix that. So that is actually at 0.4. So I guess we might have changed the example here a bit. Okay, so some further examples on cost lines for specific classification systems. So first of all, we can ask ourselves, how would the worst classifier with an error rate of a straight 100% look like visually? Well, that's really easy, because in that case, FPR and so false negative rate and false positive rate would be 1. So we now connect these two dots here, and this dotted line is the classifier that misclassifies everything in our data set. We can also ask ourselves what's the perfect classifier. Well, the perfect classifier doesn't do any mistakes, so it has 0% error rate, which means the false negative rate and the false positive rate are both 0, so that would live on this line here. Now, what are trivial classifiers that always spit out a positive class and which always spit out a negative class? Let's maybe kind of construct just one of the two. So yeah, if we have a positive trivial classifier, we would be at this point here. So I guess we have to now remember where we need to go. So yeah, so the false positive rate would be 1 in that case, and 1 minus TPR, which is here, would be 0 in that case. This is for the classifier that always predicts positive classes. And here we have the guy that always predicts negative classes. So, and now for realistic classifiers that do something hopefully reasonable, you can see here a bunch of different lines for hard label classifiers that result from classifier A or B being thresholded at different values. And we now get these different lines. And the last thing we now want to do is we want to consider all of these different lines together when we go through all potential thresholds for a certain probabilistic or scoring classifier. So how would this work? So on the left-hand side, you will now see the ROC space that we already know and have hopefully understood quite well. And on the right-hand side, we will see the corresponding cost lines for some points in this ROC space that we are considering. So first of all, we can start by thresholding at, so let's say it's easier to kind of consider a probabilistic classifier. So we can threshold at 0 and we can threshold at 1. And then we get exactly these 2 points here, kind of two trivial systems. This is exactly the stuff that we discussed before. So systems that predict are always a 1, so that are kind of totally liberal in terms of predicting the positive class. That would be if we threshold at 0. And systems that, so let's check that again, right? So we have here this guy would be, we threshold at 0, and this guy here is I think we had like a C for threshold, right? So this would be C equals 0, and this would be C equals 1. And what we will now do is we will simply move through different thresholds, kind of on a fine-grained grid, as we have done to produce our ROC curve. So if we now go from, if we now go through different thresholds, we will produce different points here in our C space, and for each of these points we can now generate a new cost line, which we will plot on the right-hand side. We will now do this for more and more and more points, and at the end we get this kind of spectrum here of different cost lines. And in order to define now our cost curve, to kind of finally reach the goal here of this little subchapter, the only thing we will do is we will now, for every prior probability, so for each setting of pi plus, we'll simply consider the pointwise minimum of all of these curves. So we kind of take the lowest point. This is why we call this also the lower envelope of these cost lines. And the resulting curve, if we take all of these pointwise minima, this is our cost curve. And this basically tells us the lowest So for every given pi plus setting of a prior probability, it tells us what is the minimal misclassification cost we can reach if we allow ourselves to vary the threshold, and why shouldn't we allow ourselves that. So this is the smallest output, the smallest potential performance value we can reach in, shouldn't maybe say misclassification cost, in terms of misclassification error for this given setting of a prior probability. So here for pi plus equals 0.25. And what we'll now do is we'll generate that to general cost matrices in the upcoming section.